Hello and welcome. Have you ever wondered why certain substances, like salt, form crystals while others, like water, don't? Or why atoms combine to form molecules? Well, that's the magic of chemical bonding. Chemical bonds are the forces that hold atoms together in molecules, making them stable. Imagine a family where each member plays a vital role, just like how atoms come together in a molecule to create a stable unit. In chemistry, understanding why atoms combine and the forces at play helps explain how the world around us is built at a molecular level. Let's dive into this fundamental concept and explore how atoms combine to form stable molecules.
Now, you might be wondering, why do atoms bond in the first place? Well, atoms bond to achieve a stable state similar to the noble gases like neon or argon. These gases have a full outer shell of electrons, which makes them extremely stable. In fact, atoms of other elements often borrow this stability by gaining or losing electrons to mimic the electron configuration of noble gases. Take sodium, for example. When sodium reacts with chlorine, sodium loses an electron and chlorine gains it, both atoms achieving a stable electron configuration. This is how nature strives to create stability, and it's a key concept in chemical bonding. In 1916, scientists Kossel and Lewis made a groundbreaking discovery in chemical bonding. They proposed that atoms bond to achieve a full outer shell of electrons, either by transferring or sharing electrons. Lewis, for example, pictured atoms with a kernel, the nucleus plus inner electrons, surrounded by an outer shell that can hold a maximum of 8 electrons. This octet rule became central to understanding how atoms bond. Imagine this like a puzzle where atoms are trying to complete their outer shell, much like filling the corners of a cube with 8 electrons to achieve maximum stability. So, atoms either share or transfer electrons to complete their octet and achieve this stable state. Let's take a closer look at how atoms actually bond. In ionic bonding, like the case of sodium and chlorine, sodium transfers one of its electrons to chlorine. This transfer results in sodium becoming a positively charged ion, Na+, and chlorine becoming negatively charged, Cl. These oppositely charged ions are then attracted to each other, forming a stable ionic bond. It's like a magnet where opposite poles attract, a simple yet powerful force that holds these atoms together. The ionic bond, in this case, is a result of this electrostatic attraction. This explains why sodium and chlorine, which are reactive on their own, can form the stable compound NaCl, commonly known as table salt. Not all bonds are ionic. In some molecules, atoms share electrons rather than transferring them. This is known as covalent bonding. Take the hydrogen molecule as an example. Two hydrogen atoms come together and share a pair of electrons. By doing so, each hydrogen atom completes its outer shell, achieving stability. This kind of bond, where electrons are shared, is the essence of covalent bonding. And it's not always just one pair of electrons. Sometimes, atoms share multiple pairs. For example, in carbon dioxide, each carbon atom shares 2 pairs of electrons with oxygen, forming double bonds. This sharing of electrons leads to the creation of stable molecules, and it's how we form the world of organic and inorganic compounds. So, let's quickly review what we've learned. Atoms combine to form molecules to achieve stability, typically by gaining, losing, or sharing electrons. The Kossel-Lewis approach laid the foundation for understanding how this happens, introducing the idea of the octet rule. Through ionic bonding, atoms transfer electrons to form stable ions, while in covalent bonding, atoms share electrons to fill their outer shells. This knowledge of bonding not only helps explain the structure of molecules, but also the behavior of substances in nature. Chemistry isn't just about formulas. It's the invisible force that shapes everything from the salt on your food to the air we breathe. I hope this session helped you see how chemical bonding works in the real world. Catch you in the next class, where we'll uncover more chemical mysteries.